Optimisation. So we're in the week now of the most busy applications we can have that seem relative to real life. Now, obviously it's not real to everybody's life, but it could be real to you if you are dealing in some sort of business or career where you are looking at optimizing or maximizing or minimizing things. So what happens is you've worked out some sort of equation that gives you a result in something, and you're trying to minimize or maximize risk or optimize it. All right. Now we're going to start with the basics first, which is the fact that differentiation is really about anything that is differentiated gives you the rate of change. All right. So if you're looking at the rate at which something is changing, that equation will give you the rates at any point in time. So normally over time, not necessarily over time though, you could have the rate at which the area of a puddle is changing by the speed of the drip that's dripping into it. You know, there's all sorts of weird and wonderful things that they can ask you. So ultimately this has got a bit of a way to go, but we're going to start with just optimizing and finding maximum and minimum of application problems. All right. So what does it mean? It means finding the maximum or the minimum. So any equation, any derivative of an equation represents the rate of change. So if we dealt with graphs and things, and we know that the rate of change for graphs is the gradient, so we've dealt with it in a pure mathematical sense as far as a graph is concerned. Now we're going to try and deal with it in the form of some sort of application. So to find the maximum minimum, we need to use dy by dx to find the turning point. So it's still relative to our graph conversations, and the fact that the turning point is usually a maximum or a minimum. All right, what's the other thing it can be? A point of inflection, which isn't very helpful to us when we're trying to optimize something, because it's not the going on that we want to do. We want to find out if something has reached a maximum price, yes, we should stop there, reached a maximum distance, right, that's what that is, or a minimum. So a little breach in the way or a stationary point isn't actually that much use to us. So we call these the critical values. Critical point, critical value, same thing. So a little bit of a change in language, but not really. To find out whether it is a maximum or a minimum, what do you think we do? Good. We use the second derivative test. Can I just say where possible? Because sometimes when we've differentiated the first time, we get something that's so revolting, we don't want to differentiate again. So where possible, we use the second derivative test for d squared, dy squared by d squared y by d squared y by dx squared. Is it? Is that right? It's all right. I don't know. One goes in the middle. Yeah, that's the one. And if that is greater than 0, we have a minimum. Backwards from what you think. And if it's less than 0, maximum. Oh, good job. All right, so minimum and a maximum. Okay, so that sets out what we actually have to do. So let's have a look at an example of what kind of thing we're looking at. So the temperature of burning rubber on a car, tire, is modelled by, modelled means it's not an exact thing, but it's close enough that we can be happy using a model. All right, y equals 20t, I didn't make this one up, I don't know where I got this one from, t squared plus 4 plus 30, where t is in seconds.
And y is the temperature.
And y is the temperature. All right. So our question is, what's maximum temperature? Find the maximum temperature. Now, I know, and some of you will know, that there are ways of doing this in physics that are not using mathematics, but you're doing a differentiation paper, and it's very, very likely that in every question you will be expected to differentiate, okay? So if you can solve something using something else, probably good, but it won't be the mathematical solution, okay? And it's not likely to be the same either, depending on what's being used. I don't mean it'll be largely different, but we're using a model, and in physics sometimes they use the change in something over the change in something, which is to use an average over a period of time. We're using instantaneous change by using differentiation, okay? So this is when physics and maths and chemistry start to really tie together, because to be a good physician or chemist, you would have to be able to apply differentiation to solve your formulas. All right, so we want to differentiate first of all. dy by dx equals. We're going to go with using the quotient rule. All right, we don't have to worry about this guy out here because he's going to vanish, right?
Oh, yeah.
So we're actually only interested in that much of it. So we're going to use f dashed of g plus g dashed of f over g squared. So f dashed is 20 times g is t squared plus 4, and it's a minus g dashed 2t and 20t all over t squared plus 4 squared. Right. So we want to know when that is equal to 0. Now, quite often in the paper, in the actual exam, they will ask something like this, because they're testing you on something else as well. What are they testing you on?
I think I might do
If you understand how fractions work. So when is a fraction equal to 0? When the numerator is equal to 0. So we can just forget the denominator, making this actually quite easy. All right, that's just not even a part of our discussion. Okay, so we're actually only solving the top, because 0 over anything is 0. All right, so this is often what they will do. They'll end up with a fraction, and they're testing to see if you know which part of the fraction. So if there's 0 on the bottom, what have we got as an answer? Undefined, right? There's no such thing as a fraction divided by 0. It's so big, how many times can you take 0 away from something? Spend a lot of your life thinking about that, right? That's what the definition of division is. 3 divided by 1. How many times can you take 1 away from 3? right? 6 over 2, how many times can you take 2 away from 6? 5 over 0, how many times can you take 0 away from 5? A lot of times, if you really want to spend your time doing that. Right? That is why it's undefined. Okay, so when this equals 0, then this 20t squared plus 18 minus 40t squared has to be equal to 0. All right, numerator equal to 0. So that is.
So if you did put it over the denominator as well and had it equal to 0, would you mark down for that or not necessarily?
Well, as soon as you times by your denominator on
It'll get rid of
0
it
times
anyway.
by it, you got rid of anyway. So
Yeah. It depends on how you dealt with it. Probably not if you dealt with it properly. So t squared equals 4. So t equals?
-2 or 2.
Good. -2 or 2. Don't forget the -2 part. All right. So at t equals at -2 seconds?
Yes.
No. Not an answer. All right. So maximised at t equals 2 gives us y equals 40 over 8, which is 5.
Why are you calling it the max?
Good question. Why am I calling it the max? I don't know it's the maximum, do I? That could be the minimum. So we might need to find out. All right, so test for max. Now, am I going to want to differentiate this again? Of course I don't want to, because it's revolting. I could simplify it and get something over something, and then I'll still have something quite revolting. Keep it. Why is y in seconds? It could be in degrees Celsius or something. No, temperature. It's not very high in degrees Celsius, but anyway. Plus 30. Good. I missed that bit altogether. 35 seconds. That makes way more sense. Good. That seems to be quite a high temperature for burning rubber. All right, so test for maximum. We want to find the second derivative of this or not. So what's our other way of finding it? Right. Test close to values. So this one's not friendly. So we'll go with and as long as we haven't crossed the borderline to another turning point, this will give us it. So the other turning point was at -2. It's quite likely to have been the minimum, but we'll carry on. So this one's given us 0. We need to put 1.5 into our derivative formula. So you get a positive when you put 1.5 in, you get a negative when you put 2.5 in. It doesn't matter what value it is, it's just about what the gradient is. So you've got a positive gradient, a 0 gradient, a negative gradient, therefore you've got a maximum point, or a local maximum point.